My name is Dan Cziczo. I'm a professor at Purdue University in the Department of Earth, Atmospheric, and Planetary Sciences. I'm the principal investigator, the lead on the particle analysis by laser mass spectrometry next generation instrument, but for short we just call it PALMS-NG. So this is what we call a single particle mass spectrometer, and so that's quite a mouthful. So in more simple terms, what we're looking at is particulate matter, small particles in the Earth's atmosphere, and we're trying to create a chemical fingerprint of those particles so we can try to understand what they're made from and where they come from. So for example, are they made of mineral dust? Are they from the southwestern US, or are they coming in from overseas? Are they maybe something like black carbon, which people know of as sort of like diesel soot, or the soot that comes out of an engine, something that comes from an industrial process. Or maybe they're a natural particle, like a sea salt particle from the ocean. And so this instrument is able to tell us that, and we're able to get a budget of the particulate matter in the atmosphere, an understanding of what comes from human sources and what comes from natural sources. So what you'll notice first of all is that this is, it's a very busy instrument. There's a lot going on here, but that's important because we're going to put it in the nose of the aircraft, and so it has to be rather compact in size. It also has to be rather lightweight, and so we've tried to jam all of the parts together into a very small package, but I can kind of explain what the major parts are for you for a moment. So in the center of this instrument, what we do is we bring in particles from the atmosphere, and once we go outside and start to install it in the nose, you can see that there's an inlet on the aircraft, and that leads to the center of the instrument. And so we bring in particles there. We bring them in by using a set of vacuum pumps, so we have a lower pressure in the instrument than there is outside in the atmosphere, and so that'll draw air as well as particles into the instrument. Once they get inside, we detect them with a series of lasers, and those lasers are inside of the black boxes here that you see, and that's for safety. We don't want the laser beams coming out either in the laboratory or on the aircraft. What happens is that the particles are brought into the instrument and they cross the laser beams, and so this is something that I think everybody can relate to. If it's a sunny day in your house and maybe you were just dusting, you can see the little dust particles in your house reflecting sunlight. Well, we do something like that inside of this instrument as well, but we bring those particles across the laser beams, and it's a much more precise way of seeing them. Once they cross the laser beam, they scatter a little bit of light, and we have some detectors in the instrument that can see that small amount of scattered light. It also tells the instrument that there's something there to analyze, and when that happens, a second type of laser, and that's inside of this aluminum box that I'm standing in front of here. This is an excimer laser. It has a very short wavelength. What that means is you can't actually see the light from this with the human eye. It's also very powerful, and that's fired. It's pulsed. It's triggered to hit the particle, and then it's going to ablate that particle, and it's going to make it into ions. And we can then manipulate those ions inside of this instrument. And what we do is we extract the negatives in one direction and the positive ions in the other direction. So it kind of gives us, I said, a fingerprint. It actually sort of gives us two fingerprints. Some things like to make positive ions, like metals, more. Some things like to make negative ions, more like sulfates. And so the positives go one way and the negatives go the other way in these two silver boxes right here. And so at the end of these boxes, we're able to detect those ions, and we get a negative and a positive mass spectrum for each particle that we analyze, essentially two fingerprints, and that tells us what those particles are. The rest of this, you can see all the cabling and the other components. There's a very small computer in here that is able to operate at very low pressure and very cold temperatures, the things that we encounter in the upper atmosphere. There's a number of unique power supplies, things that we use to power the mass spectrometers on here as well as the lasers. So these also have to operate at very cold temperatures and very low pressures. And then the cabling just sort of knits everything together. It gets the power where it needs to be. It brings the signal out and puts it on the computer so that when the plane gets home, we can download all of that data and look at it. And then this year, we actually also communicate with the aircraft and send a lot of that data back in real time, so we can actually see what the instrument's doing, see how the performance is going while we're actually in flight. And we have some ability to change a few things while we're in flight. So if we see anything go wrong, or we see that the performance isn't quite what we want, we can tweak those parameters.
Always easier to put it back, I think.
So I said that it works at low temperature and low pressure. And so one of the things that they're doing right now is that there's a small instrument on the bottom of this, and we found it was getting too cold. It's got a fan, so like if it's in the lab, right, it gets really hot. Well, in the plane, the opposite happens. It's like freezing cold, and so we're basically just like making sure that it doesn't keep blowing cold air across the instrument.
All over planes all the time. Should be good.
Well, it's just, it's a test.
Oh, okay.
So it won't be a big deal if...
Okay. So after tomorrow's flight, it doesn't work, remove it, I guess, right?
Yeah.
Yes.
If it works, we'll leave it on forever.
So we're all good. We have the laptop there.
Nick gave you the laptop, the checklist. There was the Ethernet cables in there, so I think we're good to go. No, we'll get the nose in, or the instrument in first. Thank you.
So I'm Justin. I'm working with Dan at Purdue, a research scientist. And so we built this together, and now it's time for us to upload in the nose. And as soon as it's properly installed and that the crew helped us, checked everything, we will be able to bring the instrument and the nose next to the plane. And finally we do our power check and make sure everything runs and that we are ready for tomorrow.
All right, Justin, I'm going to pull the breakers on it.
You want one?
Sure.
You will have to check around.
I got this.
Get this side. You want this side one?
Oh. Hang on. I don't want to bash into that. So we basically made Dan pull it out and put it in on his own.
I don't know about the other side.
We're above.
How's that look, guys?
On the slide or?
Yeah. 1, 2, 3.
All right, stop. I need to go up.
Okay, hang on. How's that look?
It's not bad, no?
You want me to move it over some, or? Yeah, there we go.
Okay. Here we go.
All right, let's go in. Let's have Justin do a quick check. Hang on.
Okay.
How's it look, Justin?
You good?
Yeah, here it's good.
Okay.
Okay, we can go a bit. Okay, wait a minute.
Hang on. We're going to go just to the last tire, and then Justin will do one final check, okay?
Okay, we're good with
Okay,
G
perfect. All right, hang on, guys. Hands free. I'm going to drop the cart.
Okay, you want me to check before?
Yeah, go for it, Justin. You give us the all clear.
Yeah, I think we're good.
Good? All right, cart's dropping. Hang on. 1 sec.
Yep.
All right, cart free.
Got it. All right, ready? 1, 2. Ready?
Yep.
Nice.
Perfect. Thank you.
So what we did is we just put the Palms NG instrument into the nose, and now we have to go through a series of checks to make sure that all the inlets and everything are hooked up. We actually share the nose with 2 other instruments. One is a particle counter called POPS from Harvard. The other one is a set of meteorological measurements, winds, temperature, pressure, altitude, that type of thing, and that's an instrument from NASA. That instrument is already in the nose, but we're about to install the twin instrument or a sister instrument for the Palms instrument right now. Welcome back. So the last time that we saw you, we were in the field in Kansas while we were flying our instrument. So this is the instrument that you saw while we were in the field, and we're now back at Purdue University in our laboratory on campus. So what you see is that the instrument is in largely the same configuration. It's in a different cart that makes it a little bit easier to work on. What we're doing right now is we're trying to do what we call post-mission calibrations. So the idea behind a post-mission calibration is just to make sure that the instrument was functioning the way that we thought it was, that that everything was working well. We get things like detection efficiency from the instrument. We look through performance checks and things like that. So you can see a bank of instrumentation in the back. We're producing some small particles that are of known composition and known size. We run them through the instrument and just make sure that the instrument was doing everything correctly while we were in the field. So that's really important. It's almost as important as the data that we collect in the field because it gives us confidence in that data that we really were measuring what we think that we were looking at. So that's one important aspect of what we're doing. The other important aspect is actually on the computer, so not as easy to show. It's looking through the data that we acquired in the field, trying to understand what we were looking at, if there were any big scientific discoveries. And so as we talked about when we were in the field, one of the things that we were looking at are these powerful thunderstorms that occur over the Midwestern US during the summertime. So anybody that's been in the Midwest, in Indiana where we're at Purdue are familiar with these. Intense storms, thunder, lightning, a lot of precipitation. And so we were looking at the particles that are left behind by these powerful thunderstorms as they reach into the second layer of the atmosphere up, what we call the stratosphere. And so that was one of our major objectives. And so we've done our first cut on looking at that data. One of the very interesting things, probably that the viewers won't be surprised to hear, is that we were finding a lot of biomass burning this summer. And so people have heard about the intense wildfires around the US. The last few fire seasons have been very intense. It's been very hot, very dry. We've had a lot of this natural as well as anthropogenic human-caused biomass burning. A lot of particles are left behind. People can view these as smoke plumes, but they're left in the atmosphere, and these intense thunderstorms are actually entraining them. They're grabbing those particles in the lower atmosphere. They're bringing them up as the storm moves up to the stratosphere and then leaving them behind in the stratosphere. So that's one of the huge things that we're going to be looking at. We're also going to be looking at some lesser events, things like the chemistry that's going on that occurs at the very low temperatures and very low pressures in the stratosphere. Things like halogen-based chemistry, things that aren't typically going on in the troposphere. So we're starting to look at those particles as well. And then the final thing that's something of personal interest to me is meteoritic material in the atmosphere. So it is very rare that we get opportunities to fly this high in the atmosphere. And something that's near and dear to my heart, a project that I've worked on for a long time, is looking at meteorites that are ablating in the upper atmosphere. And so probably if you go out at night, you can see these shooting stars. That trail that's left behind is actually parts of that meteor that are ablating and being left in our atmosphere. And that material sort of slowly rains down and forms small particles in the atmosphere. And this year we got high enough in the atmosphere that we were able to see this meteoritic material. Not only that, we were able to sort of profile it from the stratosphere upwards in altitude. And then we were in Kansas, in California. We actually intentionally did flights to the north and to the south. So we got a large latitude range that we were able to look at these small meteoritic particles in the atmosphere. So it gave us sort of an unprecedented ability to map these particles much higher in the atmosphere and across a much more broad latitude range than we've ever had before. So we're going to be looking into that in detail, trying to see if there's any differences by location and by altitude for these particles, and then really sort of diving into their chemistry, what they look like they're doing in our upper atmosphere. So yeah, that's pretty much the summary of what we've got going on. So I think the take-home point that I'd like the viewers to know is that it's not just about going in the field and collecting data. There's really a lot that goes on afterwards. You really have to take these complex instruments home, make sure that they were behaving properly to give you faith that they were working, and then you have to jump into the data and start looking at it in great detail. And so, a field campaign might last 2 or 3 months, and we might spend the next 2 or 3 years looking at this data and making sure that we understand what it is, what it's telling us before we can really present it with confidence.